Hello. So, in uh, in this video, I'll be explaining about the important classification metrics we have. So, first, what is classification? Classification is a supervised learning task where we predict which category an observation belongs to based on its feature. So, the goal is to predict the class of the particular uh, variable. So, and the real world case, it can be used in healthcare to diagnose diseases, fraud detection in finance, spam filtering, and product classification, like that. So, these are the areas where we can use classification. So, and then there are two types of classification, which is uh, binary classification. It means it has two classes, yes or no, positive, negative, 0, 1, like that. The example can be, is this email a spam or not? Then we have multi-class classification, which is 3+ mutually exclusive classes. So one label per sample, and the class don't overlap. Like, if example can be which digit is this, and it can be 0 to 9. So these are particularly different exclusive classes. Then we have multi-label classification, which is multiple labels per sample. So sample can belong to multiple classes and the classes can overlap. So the example can be movie genres. So a movie can be an action and romance, and another can be an romance and comedy. So the classes can overlap. So that is called as multi-label classification. So initially we're just doing the setup, then we are creating a synthetic data set. So why we are creating a synthetic data set is we want a controlled environment, and it should be reproducible. Like same seed, a random seed should create same results, and we can adjust the complexity also. So we can tune the class imbalance, noise, etc. We'll create a binary classification data set simulating a medical diagnosis scenario. So class 0 will be a healthy patient and class 1 will be a patient with a condition. So we are just setting the random state as 42, and we are just randomly creating the data. Now the data has been created. We have created total 1000 samples and with 10 features. Then for class distribution we have healthy 692, and with condition we have 308 records. Here you can see the distribution. Yes, so these are 69.2% we have healthy samples, and 30.8 we have conditions. Then the first step is to split the data into test and training data. So for training we will use 70% of the data. For testing we'll use the 30% of the data, and we are stratifying the data based on the output, because we want the same class distribution in both the training and testing set. So yeah, this is how we are splitting the data using the scikit's train test split method. And after splitting, here in the training data you can see the distribution. It's similar, very similar. 69.1% healthy records in training and 69.3% healthy records in test, and same with the condition samples as well. Now we are using a logistic regression here. It's a very simple but effective classifier that also gives low probability scores. So here we are creating the model, then we are fitting it, and then we are creating the predictions and prediction probabilities. Now predictions are made on 300 samples which we stored for testing, and this is the fine and we are storing the data in the results_df, and this is how the data sets looks like. The actual value, the predicted value, the probability, and its correctness, whether it's correct or not. Here Now, so this is what we have accomplished so far. Now, these are the key variables which we will use for the next task, which is y underscore predict, y underscore test, which is the actual label. Y predict is predicted label, which we have predicted using our model. Then we have y probability, which is predicted probability. Now let's look at the confusion matrix. So like the confusion matrix is like it has 4 fundamental outcomes, which is true, positive, true, negatives, false positive, false negatives. And let me just have, yes. So confusion matrix is a table that visualizes the performance of a classification model by comparing predicted labels against actual labels. Why confusion? Because it shows the model gets confused between classes. So yeah, it can be a 2x2 structure for a binary classification. So predicted, like one side has actual values, one side had predicted, one side actual negative, actual positive, predicted negative, predicted positive. So whenever it's an actual negative, but and we have predicted negative, it is true negative and true positive. And whenever like we have predicted it correctly, we use we call it as true, like it predicted it correctly. And whenever we are not predicting it correctly, we just add false, which is, and what was this was a negative value, but we predicted as positive, so it's a false positive. And it was a positive value, but we predicted as negative, so it is false negative. So it's this is how it looks now. Yeah, so for true positive, the example can be a patient has a disease and test detected it, which is like correct value. True negative will be a healthy patient tested, test confirmed it. That is true negative, that the disease is not present. False positive is a patient is healthy but the test said it diseased. And false negative is a patient is diseased but the test said that it's healthy. So this false positive in the disease case will be a false, can be called as a false alarm. And when the disease is there but it is not detected, then we call it as a miss. Yeah, so just the trick is, whenever the prediction is true, we call it true. When the prediction is wrong, we call it false. And the second word is what did the model predict. So if it created for a positive value but it was a negative, then it's false positive. But if the alternative is false negative. Now this is how we compute the confusion matrix. So we just use this method from the scikit-learn confusion matrix, and we just provide the test and the predict, because these are the two values that are required. And this is how the prediction matrix looks like. Now yeah, it's just the better visualization. Here you can see correctly how many are true negatives, how many true positives, false negative, false positives, like that. Another way to look at the confusion matrix is heat map. So basically the 4 columns, 4 cells which we have, and the color of the color is the count of those classes. So here you can see it's true negatives are 187, true positives are this. We missed for 40, we missed 40 records, and there were 21 false alarms. You can read it like that. So in statistic, we frame classification errors as hypothesis testing. So error type 1 error. So there are two types of error type, which is type 1 error, type 2 error. Type 1 error is false positive. Basically, you rejected a true null hypothesis, which is false positive. Then we have type error 2, which is false negative. So you fail to reject a false null hypothesis. So the main question which usually comes is which error is worse. So the answer is always depends on the problem. So different domains have different tolerances for false positive versus false negatives. So where false negatives are worse is cancer screening, fraud detection, airport security, disease outbreak. Here you don't want a lot of misses. So here false negative is worse, and where false positive are worse is email spam filter. Like an important email is a spam, then you missed that opportunity. Criminal justice, drug testing, hiring algorithm, rejecting good candidates can be false positive, critical. So yeah. Yes. So here we are just looking at the probabilities of each case. Now, based on the four fundamentals which we have, we can derive the actual positive rate, actual negatives, predicted positive, and predicted negatives. And these are relationship form the foundation of all the classification metrics, which we will look at in some time. So here are n is the total number of samples is all the records, which is true positive, negatives, false positive, false negatives. Actual positives are which are actually positive. So the true positives which we predicted correctly, and also the false negatives are positives. Actual negatives on the other hand is this. Predicted positives are true positives plus false positive, like that. So we will need this to calculate the other metrics which we use. So the first one is accuracy. So accuracy is a proportion of correct predictions out of all the predictions made. So it is correct predictions divided by total predictions. So correct predictions, we just saw that it will be true positive plus true negatives, which the model has predicted correctly, and divided by the total number of predictions. So yeah, on the other hand, the intuition is out of all the predictions I made, what percentage were correct. It is for both the classes, true and positive. So this is how we calculate the accuracy. But if we want it higher, this value, and it's very simple to understand and calculate, but it can be misleading, which we will soon in some time. So this is how we are calculating the accuracy. So in the earlier model which we have, the accuracy is coming as 79%. So this is actually a manual calculation. We can also use the scikit-learn's accuracy score, which does the math under the hood. You don't have to write the formula. But yeah, so now let's see when accuracy works well. So accuracy is a good metric when classes are balanced, so roughly equal number of positives and negatives, and both types of error are equally important. So false positive, false negative have similar cost. You need a quick simple evaluation, then we use it, but it won't work if it is imbalanced classes. So the problem, the accuracy paradox occurs when a model achieves high accuracy but it actually useless or even harmless. So this happens with imbalanced data set. So when one class is much more common than the other. So for example, the fraud detection, imagine a credit card fraud detection system. So 99% of the transactions are legitimate and only 1% of the transactions are fraudulent. So the model always predicts legitimate achieves 99% accuracy but catches zero fraud. So here in this case, it did not predict the 1%, but because of the induction of accuracy, the accuracy will be 99%. So here we won't use this matrix is not useful in this case. So this is just the demonstration of the same. So the paradox is the dumb model has a higher accuracy, but it catches zero fraud, so it's completely useless. Oops, sorry. So for that we have balanced accuracy. It's a better alternative to the normal accuracy. Balanced accuracy is the average of recall obtained on each class. So the formula goes like this: 1 divided by 2, which is, this is sensitivity and this is specificity. So why it's better, it gives equal weightage to each class regardless of size, and a model predicting all of one class gets 50%, not 99%, and better reflects actual model performance on minority classes. So again, here you can use scikit-learn's balanced accuracy score, and now we'll use the same accuracy model. Here you can see the accuracy is coming as 99%, but the balanced accuracy, you can see here it is showing us 50%, and here it is. So, and it's actually useful here. And now let's see when to use and not to use accuracy. So accuracy when classes are balanced, both error types have similar cost, and you need a quick baseline metrics and comparing model in the same balanced dataset. We avoid accuracy when the classes are imbalanced and one error type is much more costly, working with rare event detection, and you need to understand both class performance. Now let's look at precision and recall. So precision is when I predict positive, am I right? So this is the question which precision asks, which is, when I predict a positive, am I right? So it's a positive predict. It's also known as positive predicted value. It measures the accuracy of positive predictions. So the positive predictions divided, like two positives divided by all predicted positives. So the intuition is, of all the samples I predicted as positives, how many were actually positive? Excuse me. And that's the formula for it. And here in the model, we are getting the precision as 71%. Now let's look at the recall. So recall is, did I find all positives? Is also known as sensitivity, which is positive to positive rate. It measures the ability to find all positive samples. So it's more like two positives divided by all actual positives. and here it is true positives by all predicted positives. So whatever I have predicted, how much were correct, that's precision. And this is of all the actual positives, how many did I catch. So this is more of a sensitive metric. Now the intuition is of all the positive samples, how many did I correctly identify. So yeah, that's the formula for it. Here you can use the recall score for scikit-learn. Now let's look at precision versus recall side by side, because they both can be very confusing and very similar and confusing. So precision is quality of positive predictions of all the positive predictions I have made. How much did I correctly predicted, and it penalizes false positive. So it means high precision equals to very few false alarms. And recall, on the other hand, it is coverage of actual positive. So did I find all the positives? So it compares with the actual positives and not the predicted positives, and it penalizes false negatives. So high recall means few missed positives, and we use it in the disease detection, where you don't want to miss the positives, so you use recall in that case. So for the model which we trained, you can see here this is the precision, which is coming as 71%, and recall is 56%. So when to prioritize precision versus recall? So in most real world scenarios, you can't maximize both. So improving one often hurts the other. Think of it as a dial you can adjust based on your business need. So prioritize precision when the false positives where false positives are expensive. So like for email spam filter, you don't want to mark any important mail as spam. So here the false positives are expensive, so you look at high precision metrics at the time. And on the other hand, recall is used when the false negatives are dangerous or are expensive. So cancer screening, any disease screening, you don't want to miss any patient who has cancer but was not detected in a case. Fraud detection, security threats, COVID testing, like that. Now let's see how changing the classification threshold affects precision and recall. So when the threshold is 1%, you can see the precision is very low but recall is high. But as you increase the threshold, you will see the precision is increasing and the precision is increasing and the recall is decreasing. So that's the proportional inversely proportional relationship they both have. And we can see it over here as well, the same plot. Now we have specificity, which is recall for negative. So the earlier one which we did was recall for positive. This is recall for negative. So specificity is, it measures the ability to identify correctly identify negatives. So the formula just flips true negative by true negative plus false positive, which means which were negative but were predicted positives. So of all actual negatives, how many did I correctly identify as negative? So that's now and that's precision and recall. Now let's look at F1, F2 and F beta scores. So let's look at the problem. So the precision and recall can be misleading alone. So the extreme cases are model A, it predicts everything as positive. So the recall is 100% because it finds all the positive, and precision is very low, and because there are many false positive. So only, and there we have model B which predicts positive when 100% sure, which means the precision is 100%. So never wrong when predicting positive, and recoil is very because it misses most positives. So neither model is actually good. We need a metric that balances both. So that's when F1 score comes into the picture. F1 is an harmonic mean of precision and recall. So F1 score is a harmonic, So the formula goes like this: recall multiplied by precision multiplied by recall divided by the addition of both. Why it's harmonic? Why harmonic and not arithmetic? So arithmetic mean can hide poor performance. If precision is 1 and recall is 0, arithmetic mean is just divided by 2, which is 0.5, and it looks okay. Harmonic mean, on the other hand, is 0. It correctly shows the failure. So that is why the harmonic mean penalizes extreme imbalances. So then we have F beta, which is controlling recall, precision recall emphasis. This is the formula, and you just basically, you can be using the beta, you can control the emphasis. So if the beta value is 0.5, precision is multiplied more, and false positives are very costly, and then you just decrease the beta. But let's say recall is really important, condition can be false, where false negatives are costly, you just increase the beta. So yeah, when you care more about precision, you reduce the beta value. When you equally care about both precision and recall, which is the original F1 score, you just put beta as 1, and then when you care more about recall, you just increase the beta value greater than 1. Yeah, here you can see the threshold. When you increase the beta value, when the beta value is 0.5, the precision is higher. When the beta value is low, the precision is low. But this is when the balanced F1 score looks like. Then we have Matthews correlation coefficient, which is considered one of the single best metrics for a binary classification, because it uses all 4 confusion matrices, like true positives, true negatives, false positives, and false negatives, and it works well for balanced classes. This is the formula for it. We also have Cohen's kappa. It's an agreement beyond chance, when it measures how much better your model is than random chance. Now that we have looked at all the points, let's look at the ROC curve. So ROC stands for receiving operating characteristics. So ROC curve plots the true positive rate against the false positive rate at various classification thresholds. So on the x-axis we have false positive rate, in the y-axis we have true positive rate, and for each point on the curve represents a different threshold, and the curve shows how the trade-off between the catching positives and false alarm. So this is how the ROC curve looks like. So this red line is the worst one. You don't want to go beyond this, but the more this curve looks like this, the better it is. Yeah, here this one is the best case scenario. It's a perfect classifier, and yeah. So area under the curve is when you want to compare multiple models, like